Okay, physics, draw some free body diagrams with you. So I just thought I'd run through some examples of these and help you get a feel for it. So here we go. We have a guy and he's pulling a box. I can make two free body diagrams from this, right? So I'm going to have the box. So let's do that first. So I'm going to think about the what is contacting the box. You put a floor there to make one thing more obvious. And then what's acting at a distance, right? So what's contacting it? So here's my box. There it is. What's contacting it? Well, he has this rope, I'll call this tension, going up at some angle. They give me an angle on there. I can put that in there if I want. He's got the floor touching it, so the floor is acting to push it up, right? So it's going to be going upwards, and this will be the normal force. Remember, the floor gets bent a little bit, depressed a little bit, and then it's springing back to push the box up. And then acting at a distance, what do I have? I have gravity, so I can write this in two ways. I could say the force of gravity, and sometimes we call this mg as well. Either one is fine. You'll see both of those. So key thing, though, without the normal force, or without this tension pulling up, what would be different? So if I had just the box by itself, I would have this same force of gravity pulling it down. But the thing that would be different, right? So tension is pulling it up a little bit and to the left. So without that tension, my normal force now would be exactly the same height. In here, these two are not equal. My normal force is no longer equal to my force of gravity, right? Gravity doesn't change. So as much as I pull on a box or push on a box or lift it or drop it or whatever I'm doing to it, the force of gravity is always the same. But when I have it sitting on something, that normal force will change. So this is a free body diagram. So a free body diagram is not going to have components on it. If I wanted to, I could draw a second diagram. It would not be a free body diagram, but it'd be a component diagram. I could draw a second diagram, which would say I have this force of gravity pulling down. I have the same normal force pulling up. And I have some tension in my x dimension. And I have some tension in my y dimension. So I can break this into two forces and treat it exactly the same. This is what we'll do for statics when we get there. But notice now that those upward forces have to equal the lower forces. So it's not accelerating up or down. So it must be going. So these are things, the forces I usually want to look for. So what I want to look for contact forces. So common forces. I'm going to have my my normal force n or normal force, either one's fine. I'm going to have, we can worry about frictional force, so I might have frictional force that's on there. I want to check for my force of gravity. And these are three things that you always want to think about. So in this case, I didn't tell you about friction, so we'll assume it's a frictionless floor. If I had friction, if this was going at constant velocity, and I had friction, I would add friction in opposing motion. And then my component diagram, that force of friction, if it's moving at constant velocity, right, those force of frictions would cancel and they'd be the same magnitude. Anyway, so we use force diagrams really to help us think about things. So the force diagram doesn't have components on it. It has the original forces, the original angles, and I can draw a component diagram to make sense of things later. Let's do something more complex. So here I can have two force diagrams. So I want to be careful about this. So this force diagram, I can make one for the left box and one for the right box. I'll assume there's no friction just to make it a little bit easier. And I'll assume this is stationary. So I'm going to be careful about this. So a string transmits force from one place to another, and a pulley just changes the direction of the force. So I'm going to be careful about this. I'm going to say, well, everything going in this direction, I'm going to make positive. And then everything going sort of up, I'm going to make positive. So I'm going to be careful about this. So I'm going to draw a force diagram for this and a force diagram for this. So a couple of ways of doing this. So let me see. So I'm going to take my 30 kilogram box. I'll call this box A and this B. So here's A, right? So A is going to have tension pulling it up the hill, and it's going to have gravity pulling it straight down to the center of the earth. And my normal force, I want to be careful, my normal force is going to come off perpendicular to my surface. So for block A, it's going to look like this. For block B, For block B, well, I'm going to have the same forces but arranged slightly differently. So now I'm going to have same thing. So gravity pulling it down. So force of gravity pulling it down. I'm going to have my normal force now being perpendicular to this angle. And I'm going to have tension now going in the direction up the hill. And this is block B. If I wanted to, I could draw component diagrams. And there are a couple ways to think about this. So I could say, okay, I'm going to break my components up into X and Y components. So here we go. I'm going to have my force of gravity pulling down. And I'm going to have tension in my X dimension. I'm going to have tension in my Y dimension. I'm going to have my normal force in the Y dimension and my normal force in the X dimension. And if it's stationary, these should need to balance out, so I didn't draw these quite to scale, but you get the idea. So notice I had to separate two of these. So there is an alternative, and the alternative that we'll do is there's no reason that our X and Y has to be perfectly horizontal to our page, right? I can pretend, well, my X-axis is going to be parallel to the slope, and my Y-axis is going to be perpendicular to that. So what I'm going to do is I'm going to line my X and Y axes up with two things that are already perpendicular to each other, and that way I have fewer things to separate. So I'm just going to rotate my paper, right? So I'm going to rotate my paper, and now I'm going to draw an X and Y axis, which is going to be lining up with more forces and is going to give me less math to do. Right? So I'm going to end up having my X axes going along the tension and my Y axis going along the normal force. So briefly, if I do that, right, so now I'm going to rotate everything. So here's my box, and I'm just going to rotate that. So now my normal force is going straight up, and my tension is going straight along the x-axis. Right? But notice now that my force of gravity is going to be going off at an angle. Trick to remember, you can logic your way there, that this angle in here is going to be this angle in here. Ooh, that was kind of tricky. So you have to find a way to get the right angle in the right place, and you can right. Anyway, through congruent angles you can get there. But trust me that this angle between what's left over. So in this case, I would want to separate my force of gravity into two components on a separate diagram, and I would end up having something that's more sensible. So I have my normal force, I have my tension, I'd have my force of gravity in my x direction, and my force of gravity in the y direction. And if it's stationary, all of these should be this should be equal, and those should be equal. Okay, a couple more. So here we go. I have Tarzan's skirt got stuck on a tree. Go figure. So let's draw a diagram for Tarzan. So right there's Tarzan, looking good, right? No Jane, just Tarzan. So what are the things that are interacting with him? So he's got the tree, and the tree is acting to pull him this way. So I'm going to say this is the force of the tree. You got tension, so I'm going to say the tension is going this way, force of tension. And so he's not standing on anything. There's nothing pushing back on him. There's no normal force, but he does have the force of gravity that's pulling him down. I could separate tension into x and y. So I would have for tree versus tension. Anyway, so I'd have the force of the tree. Force of tree. I have force of gravity, and I'd have tension in the y dimension and tension in the x dimension. And if he's stationary, this is going to be the same as that, and this must have the same magnitude as that. Okay, last one, ramps. We're going to see a lot of ramps. It's a common type of question that we'll come across. So I have a skier on a ramp. So a skier, I'm going to say that there's no friction. So I'm not going to worry about friction. I'm going to say so he's moving, he's going to be accelerating, so unbalanced forces. We'll get to that in a little bit. So I'm going to have a skier on a ramp. So I'm going to draw one normal force diagram, and then I'm going to decide what I want to do. If I want to rotate the axes or separate components, I'm going to worry about that separately. So first thing, a normal force diagram. So I'm going to have force of gravity pulling down, and I'm going to have the normal force pushing up. Right? That's it. That's it. If he's going down a ramp at constant velocity, Right? That means there must be friction, and if I had friction, my friction would go in the opposite direction of motion. Okay, now if I want to make a component diagram, well, I got to think about this, right? So I can separate these two. That's kind of a hassle, but instead I'm going to rotate my axes. So my normal force is going to be lining up my y-axis friction. So I'm going to line up my ramp with my x-axis. Just makes it convenient, right? So if I want to draw a component, right, or if I want to rotate this, I say this is my normal force. This is my frictional force. Now my force of gravity is going off of this awkward angle, right? So be careful with it. And if I want to separate this into components, I would have my normal force, my frictional force, and now my force of gravity in my horizontal component, and separate my force of gravity into my vertical components, and these are going to cancel and those are going to cancel if it's going at constant velocity. So the trick with this, though, notice that this angle here is going to be this 35 degrees. Right? And we can think about how that happens, right? So here my guy is at this angle. So this is the angle that I care about here. So I'm going to draw a right triangle here. I'm going to draw a second right triangle here. Okay. So this angle across here, that angle, right? That angle is going to be 90, right? Which makes this angle inside here. Right? So if this is 35, this is going to be 90 minus 35, 55. And then that combined with the other angle, which is unknown, needs to add up to 90. So that means this must be 35. Right? So this angle inside here, I get a double one, it ends up being the same. So anyway, when you're drawing these diagrams, it's really important that you get the angle correct. And as a shortcut, just to remember that between the force of gravity and the normal, that angle is the angle of your ramp. Anyway, I hope that's helpful, and we'll talk to you soon. Bye.